What up, everybody? Welcome to another episode of Ask Paul, where we talk about the National Electrical Code, and I answer those questions that are submitted through our portal over at www.paulabernathy.com. So today we're going to get into some questions that are submitted. I have two questions that I'll be discussing today. The first question will be talking about feeder taps, and the second question will be talking about when you use multiplication or division when it comes to adjustment and corrections for conductors, for ambient temperatures, or number of current carrying conductors in a raceway. So there's a little confusion on when you would multiply versus division in helping you solve those questions. So I'll answer that question today. That'll be the second question. The first question we have on today's show is, it says, Paul, for feeders, where do we get the prohibition that says you can't tap a tap? Okay. Thanks for that question. Great question. People ask that all the time. We use these terms, what I call industry slang, when we say tap a tap, things like that. You're not going to see that language in the code. All right. It kind of says it a little different than that. It kind of makes it's kind of the way the statement is. And you have to kind of read between the lines to understand what we're saying. But basically, once you derive a tap conductor from a feeder, and he stated feeder, so we're going to go straight to the feeder applications, you can't tap a feeder, which now you created a tap conductor, which is going to bring in all these rules because you don't have any overcurrent protection at the tap. All you have is the upstream at the feeder, that you have to follow these specific rules. So it wouldn't be something where you would tap a feeder and then turn around and then tap that tap. That would be tapping a tap. Right? Now, the code doesn't say it in those specific words, but we're going to dissect it for you and show you how indirectly that's exactly what it's saying. So, first things first. When we're talking about feeders, since that's what was in the question, we're talking about the ability to take a feeder and tap that feeder with the conductors to feed something else. Okay, so we're creating tap conductors. Now, we have tap rules. You're probably all familiar with the tap rules. I've talked about them many times in other episodes. Again, you can go over and listen to our episodes over on our masterthenec.com website. And you'll see the podcast button up there. You can listen to any podcast. Or if you want to watch videos on it, check out our YouTube channel at youtube.com/masterthenec, all one word. And we have a plethora of videos. And, of course, I also push my podcasts up there as well. So if you want to listen to podcasts, it's an easy way to listen to it over on our YouTube channel. So check that out. So obviously the question is, where do we get this you can't tap a tap rule? So let's first start by the general rules. And that is where we got to have overcurrent protection for feeders. And so 240 is about overcurrent protection, Article 240. And we're trying to find out where do we place this overcurrent protection in our example. And so this takes us to part 2 of 240, which starts at 240.21. All right. Now, if you want more information on all the tap offerings that you have, then one of the things that you might go look at is 240.4E. Now, that talks specifically about tap conductors, and that's where we get the permission for 240.21, which is a location in a circuit where to have the overcurrent protection. But there are other allowances for tapping, things like tapping feeders under 210.19 when you're dealing with ranges and cooking appliances and so forth. There's all different types of applications for single motor taps under 430.53D. All of that's listed under 240.4E in case you didn't know. It's all right there. So we have been given the permission to tap a feeder. However, there are rules we have to follow. Why? Because feeders, like any other conductor, have to be protected at their ampacity. So you've got a panel and you've got a breaker in there, and that is a feeder breaker that's feeding maybe a panel downstream or something, and that's a feeder. And now we're going to be tapping that feeder. And we have to follow these rules. Okay, so there are a certain number of rules that you have to follow. So we're specifically going to answer this question about where do we get the prohibition to tap a tap. Well, in the NEC, you're really not going to get that phrase, tap a tap. It's something that we have to read between the lines. We have to understand how to read the NEC, and that can become a challenging thing for many people because we want the NEC to say what we want it to say, but it simply says what it says, and we have to be able to read it, interpret it, and understand it and apply it, right? So when we look at this, we want to always follow the main rules or the general locations of the overcurrent protection. And that takes us to 240.21. This is titled the location in the circuit where we would have this overcurrent protection. Now, I will tell you right up front, I am always using the latest adopted, I shouldn't say adopted, the latest published edition of the National Electrical Code. Now, I understand in your state, you might still be on the 2017, maybe even 2014, or heaven forbid, you're still on something even newer than that, like a 2011 or 2008. I cringe to think about that, but wherever you are, some of the rules may be different if there's been code changes. So I am fully aware of that, but don't email me on that. I am only dealing with the 2020 edition, and if it is applicable to the 2017, that is great. But you need to do your due diligence when you review these after we discuss this. All right, so this question is, where do we get the term that you can't tap a tap? All right, so let's talk first about the overcurrent protection requirements and its location in the circuit. 240.21 says, location in the circuit. It says overcurrent protection shall be provided in each ungrounded circuit conductor and shall be located at the point where the conductors receive their supply, except as specified in 240.21a through h. Okay, so the feeder is going to typically get its protection at its origin in your panel board, okay? And in that panel board, which is in the cabinet, is going to be where you'll have a 2-pole breaker, 3-pole breaker, depending on what voltage class you're dealing with. And that's going to be where your feeder is protected. That's the typical general rule. That's what we generally do. And we're going to size those conductors and going to be protected by that overcurrent device, and everything's happy. But there are allowances, obviously, when it says except as allowed in 240.21a through h. So in that case, we're going to specifically go to 240.21b. Why? Because the question said, where do we get this prohibitive allowance to tap a tap when it comes to feeders? And that's where we're going to be. We're going to be at 240.21b. Okay. Now, if you look at 240.21b, we're talking about feeder taps, and here's what it says. It says, before I even go there, let's go to the last sentence because I almost skipped it. The last sentence of 240.21, which is critical. Here's what it says. Conductors supplied under 240.21a through h, and of course we're going to be using b for feeder taps. It says shall not supply another conductor except through an overcurrent protected device meeting the requirements of 240.4. Okay, so this is almost verbatim saying, if you were to translate it loosely, is once you originate that tap, you can't tap it again. The only thing you can do is if you were to hit an overcurrent device, now you're going to have this protection on there, okay? So without saying that you can't tap a tap, basically it's saying if you use the allowances that we're going to be talking about here in 240.21a through h, that once you tap it, you cannot tap that conductor again. That would be they not able to tap a tap. And it basically says that shall not supply another conductor except through an overcurrent device. Makes sense, right? So if you're tapping it and then you can take it into an overcurrent protected device, then you're going to be limiting your load. Then that's different. You wouldn't be tapping a tap. That tap conductor stops at that overcurrent device. Now it has protection because the whole concept of this feeder tap is to be able to tap a feeder without any overcurrent protection at the point of the tap, right? So without saying it, that's what it's saying. You cannot tap a tap. But we're not going to stop there. We're going to keep on, and we're going to look at 240.21b, which is talking about feeder taps, which is kind of where this question was driven at. It says, conductors shall be permitted to be tapped without overcurrent protection at the tap. That's the whole point of the tap rule. is you're going to tap onto the load lugs on a disconnect, load lugs on a service disconnect, which once you get to the load side, it's now a feeder. Or you're tapping a conductor that's going from a panel out, and you want to be able to tap those conductors. You want to make a feeder tap. This is what you're doing. You're not going to have any overcurrent protection at that tap. This is what this rule is allowing. It says, conductors shall be permitted to be tapped without overcurrent protection at the tap to a feeder as specified in 240.21b1 through b5. So you have 5 conditions here, and you have to meet one of these conditions. It says the tap shall be permitted at any point. All right, listen to this. The tap shall be permitted at any point on the load side of the feeder overcurrent protective device. So this is all grayed out in the 2020s. So this clarified to a lot of people that were very confused. They were like, can I apply these tap rules? Does it have to be to a conductor? Does it have to be a certain distance from the feeder protection? Or can it be at the lugs itself? And the answer to that is very clear. At any point on the load side, from the lugs downstream through the feeder, I can make this tap and apply these rules. So it doesn't just have to be to a conductor. I see this probably the number one thing that when it comes to feeder taps that I get asked around the country when I was doing the live seminars and live training and at different venues, they would always be a question. Somebody would raise their hand and go, yeah, but doesn't the feeder tap rules only apply to a conductor? No, it applies from the load side of the feeder overcurrent device. Okay. From that point, I could have multiple lugs and I could apply these rules if I wanted to have different sets coming off of it, if I meet all the feeder tap rules. Okay. So that's an important statement. The tap shall be permitted at any point on the load side of a feeder overcurrent protected device. And I'm telling you, the lugs are on the load side. So that debate should always end now. Okay. It also says section 240.4b shall not be permitted for tap conductors. Okay. So 240.4b, you're all probably familiar with that. 240.4b is where you go to the next size if it doesn't correspond. Not going to work here. We don't get to jump up or do anything like that. You can't use the next size up rule when you're dealing with feeder taps. Okay. Just kind of get that out of the way. You can't do it. Now, of course, we've already answered the question without it saying you can't tap a tap. That's basically in the last sentence of 240.21. And we understand that. We're pretty straight with that. But then you've got all these other tap rules that we cover in other episodes dealing with B1, B2, B3, B4, B5 that deal with the 10-foot tap rule, 25-foot tap rule. We've got the primary plus secondary, not over 25 feet tap rule. Got a video on that. And of course, we have tap rules for over 25 feet when you're dealing with manufacturing buildings that have a height over 35 feet high at walls. And we have rules there. And then, of course, we have what's called outside tap with unlimited length as long as those feeders are outside. Those tap conductors are outside, except for the point where they enter into the building and you follow all the rules. Then we have options. Okay. So this brings me to something that's kind of, I've already answered the question, but it brings me to this. I spend, a fair amount of time looking over different social media, not so much that I chat on social media, because we have our own Sparky Hub. If you're not familiar with it, you can go to www.thesparkyhub.com and join us on there for great discussions, post your images, things, and get your answers. Great bunch of people that frequent that website. But I do go on to other social media platforms, Twitter, TikTok, Instagram, all these others. And my handle is always the @ Master the NEC. So I'd love to connect with you. Send me a connection link or whatever, and we can connect up. But I'm always on these social medias. And the reason I go there is because I like to see the pictures that people post and their responses. And I like to think that a lot of the responses I see are people that are spouting out things like that's a violation or that's a code, but they never give a code reference. It literally drives me crazy because I would venture to say that 90+% of the people that make a statement like that are wrong. They have no clue whether or not it's a code violation or not. It's just something that they have not done, or they have failed it because they thought it was wrong, or they don't really post anything to support their position. Now, I'm not here to bash them again, but I do cringe because I don't want to be that person who goes on the social medias and just tries to set the record straight on everything. Not that I'm a know-it-all, but some things I will set the record straight, but I will post code references. So it is embarrassing to see electricians in this trade, which I'm always trying to elevate this trade to professionalism, have people post comments on images that are wrong. Case in point, I'll give you an example. So in Instagram, is this a company that makes hats and things called World of Electrician. Great company, doing great things, selling great merchandise. They put a picture out once a week or a different code thing, and they want people to respond. And they put out one, I guess, a couple of days ago, maybe, and it was showing a tap in it looked like a combination meter and panel enclosure, a combination unit, and it showed an example of a feeder tap. And I can tell you that the majority of the comments on that were incorrect or wrong or just talking from their hip. And of course, if you say that to somebody, they go, well, I don't run around with a code book. Well, maybe you should stop and look it up before you just off the cuff comment and you're wrong. Now we're in that picture. They never post enough to call out all the other possible violations in there, like an unsupported cable entering the top, maybe. And then, of course, people say, well, you can't have sheathing in the box more than a quarter of an inch or something like that, which is not true. But they post that anyway, and they'll say it's a violation. So there's other things. You can't really see the grounding, the bonding. You can't really see everything. So that's why I hate to comment on images that don't give you the entire picture. But I did notice that this one, you can go search for it up on World of Electricians. You can look for it. They posted a classic example of a feeder tap. Now, I don't know all the other rules associated with that, but they were using a splice that looks like that was an isolated splice. That means that it's already insulated, doesn't need to wrap it in tape. Again, you'd have to check the manufacturer with that to see, because it does have lugs on it, but I believe those are isolated. Wouldn't hurt to wrap it in tape, though. But at the end of the day, that was a prime example of a feeder tap application. It could have gone straight to the lugs, or it could have gone straight to the conductor. It doesn't matter. So that was a classic example of using 240.21. Now, I don't know how long those feeder taps were. I don't know whether they conform to the 10-foot tap rule, the 25-foot tap rule. Have no idea. So I can't comment beyond that. But the sheer fact there was a number of people that were commenting in there, making statements up that I have no idea where they got the information. It just goes to show you that we have a lot of training left to do. There is a lot of education. Now, the problem I have with a lot of electricians is that they are so stubborn that they don't want to learn something new. They think they know it all. And I am the first one you've heard me say, I don't think I know it all. I spend a lot of time learning, but I will back up all my statements with code references. And in this example, this could have been a classic example of an allowable tap in 240.21b for a feeder tap application. And without any additional details, without any additional explanation, that's about all you can go on. Now, there's probably other things wrong in there. Some people argue that the wire space wasn't adequate enough for these splices to be in there. We would have to know the dimensions in order to be able to calculate out to see whether that was the case. But on the surface value, that's a classic example of a feeder tap application. But there was so many people posting that it was a violation, but they didn't give a reason why it was a violation. So I found that kind of one of those things where, and this thread went on and on and on and on. So go check it out. It's over if you're on Instagram. Connect with me also at Master the NEC. I'd love to connect with you over on Instagram. I don't do a whole lot with it, but every now and then I post some stuff. But again, all of my social media is the @ Master the NEC. So search for me on Twitter, TikTok. I still don't understand that platform, by the way. I don't get it. It seems like there's a lot of people that are, I don't know. Anyway, if we use TikTok, it'll be to promote our products. It's not going to be for me to share any new information. I can promise you that. All right. So anyway, that answers that question for that individual. and probably more than they wanted. But again, little extra information never hurt anybody. If you want more information on feeder taps, I have videos out there. Just go check out our channel and you'll see I have an extensive video series on transformer secondary conductors, which also fall under part 2. But that's going to be dealing with secondary conductors. And so again, if anybody's interested in that, check that out. But that's pretty much it for that question. All right, so we'll move on to the next question in today's episode. And this is dealing with when to use multiplication or division for adjustment and correction applications. Okay, so that's the next one we'll address. All right, so when we're talking about adjustment and corrections as the question, and I'll read the question fully so that we can make sure that we capture it. And then I kind of do some explaining, because there's certain things that you're not going to find in the code, and we have to address it so that you understand the concept of what's called a reciprocal. So first, let me read the question. The question that was submitted says, Paul, when I have an ambient temperature question, when do I divide or use multiplication? How do I know which one to use? Thank you for all your help and the Ask Paul platform. Okay. All right. Great question. I get this asked a lot. And the first thing I would tell this submitter was make sure that you go and visit our website and go up to the podcast or go to our YouTube channel and search for Derating Demystified. Now, that is a video that I put out a couple years ago, and there is a 2.0 version out now that's only available to our subscribed members on our YouTube channel. You have to be a subscription member to join, where you pay $9.99 a month. Small price to pay for all that private content, but that is where you get the updated edition or version. But 2.0 or the original version goes into detail about adjustment and corrections and how to do it, and when you would use division, when you would use multiplication. So first thing, for a more intense explanation, I encourage you to go check out that video. You can find it. Just go search for Derating Demystified, and you should be able to find it on our YouTube channel. Our YouTube channel is youtube.com/MasterTheNEC, all one word. And of course, if you're following us on any of our social media, again, it's at MasterTheNEC. You can follow us anywhere and get that information. All right, let's talk a little bit about what's called reciprocals, so that you can understand when we're going to use the general sense, because he's talking about ambient temperatures. So it tells me that he's going to be doing adjustments or corrections, and he needs to understand the reciprocals. And 125 is the same as 80%, depending on how it's used. Now, we can quantify that very simply, because the code is going to tell us the need for 125% for continuous load, or full value, or whatever the face value is of the load at a non-continuous. Now, where you get all this information first is that you have to go to 210.19. Obviously, we're talking about branch circuits here, but you look at the general rules in 210.19A1, and that tells you that we have a branch circuit supplies continuous load, or a combination of a continuous and non-continuous load, that it's 125% of the continuous load and 100% of the non-continuous load. Okay. So continuous loads are defined in the National Electrical Code. And so to understand what that means, you got to go look at Article 100. And when we look at 100, we say, okay, I need to know what a continuous load is. And it is a load where the maximum current is expected to continue for 3 hours or more. So that's critical. In order to be able to be considered a continuous load, we're talking about the draw has to be the maximum current draw on that circuit continuously for 3 hours or more. Not intermittent, not cycling, not something like a range where it cuts on, cuts off burners. It's never going to be at full maximum current for 3 hours or more. It's always going to be cycling on and off. That's why ranges are not considered a continuous load. Okay. Now, people ask about a water heater. Why is a water heater taken as continuous load? It is for sizing the branch circuit to it, because the code tells us that under 422, right? But in reality, it's cycling between the top element and the bottom element, And it wouldn't necessarily be the rule of the continuous load because it's running at its maximum value for 3 hours or more, because you either have the top element on or the bottom element on. It's not its maximum value. Okay. So it cycles. But the National Electrical Code specifically tells me when it comes to branch circuit sizing to take a water heater as a continuous load. And that basically just says treat it at 125% for conductor sizing and whatnot. All right. So it is not a continuous load in a sense that it's 3 hours at its maximum current. Okay, so usually I clear that up for people right up front. Now, in all of these, you see us talking about continuous loads, or when we treat it as a continuous load at taking something at 125%. Well, you have to understand that there is a reciprocal of 125%, and that is 80%. Now, people ask all the time, Paul, where does it say 80%? Because we hear it all the time. Where does it say that in the NEC? It does not. You have to understand that through your learning, your training, your core fundamental training, that is the reciprocal of 125, depending on the values that you're given in the question or even in reality. So I'm going to give you some examples. So the question is when you use multiplication or when you would use division. So let's start out first by understanding the reciprocal. Why does 125% a reciprocal of 80? Well, let's look at it. So if I've got a 20 amp overcurrent protective device and I cannot load that device more than 125%. So I've got to limit the current on it to 125% onto that breaker. So I've got a specific continuous load that's being applied as a load on these conductors. So let's just take a 20 amp overcurrent device. So since I have to limit it, okay, to 80%, and you're saying, again, where does the code say 80%? Well, it doesn't. What you have to do is look back at 210, and now we would jump to 210.20. Now, 210.20 says, branch circuit conductors having equipment shall be protected by overcurrent protected devices that have a rating and setting that complies with 210.20 A through D. You with me? Okay. What does A say? It says where a branch circuit supplies continuous loads or any combination of continuous and non-continuous loads, means you take the continuous at 125 and 100% of the non-continuous. It says the rating of the overcurrent device shall not be less than the non-continuous load plus 125% of the continuous load. Okay. So if I told you what the continuous load would be versus what the rating of the breaker is, so depending on what I'm given in the question. So I know that I cannot exceed, the breaker can't exceed 125% of, it can't be less than 125%. I should say it that way. Can't be less than 125% of the continuous load. So what is the value of on the conductor is the continuous load. So if I take the 20 and I multiply that by 0.80, which is 80%, that gives me 16 amps. So if I have something that says I have 16 amps of continuous load, then the breaker that I terminated onto, one, has to obviously protect the conductor, but two, it cannot be less than 125% of the continuous load. So we did 80. So how do we know that that is the reciprocal of 125? Well, then let's take that 16 amps and we're going to do what? We'll take that 16 amps and we're going to do that times 1.25. That equals 20 amps. So if I know the breaker and I want to find out what the continuous load that can be put on that breaker, provided that breaker is not rated for 100% rating, which is an exception. I'm just talking general molded case circuit breakers. The general, they're going to be limited to 80%, or they're going to be not less than 125% of the continuous load. Okay. Now, the next question I get from people obviously is, can I put 20 amps on a 20 amp breaker? And general, yes, as long as, one, it's not a continuous load. So I can put 20 amps on a 20 amp breaker every day of the week, as long as it's not a continuous load. Now, we're not talking about receptacle limitations and other things that are going to be limiting for receptacle applications when you know that cord and plug connected things are in it. We're just talking general statement here. Can I put 20 amps of non-continuous load on a 20 amp device? Absolutely. But when it comes to continuous load, I have to limit it to 80% for a standard circuit breaker. Why? Because chances are that circuit breaker is not listed for 100% use at its maximum rating, which is if it's a 20 amp, then it could take continuous loads at 20 amp if it was rated for that. But usually they're rated on a continuous load at 80%. Okay, so that's how the reciprocal works. Now, knowing what the conductor size we have to have and things like that, then we start bringing in the application of, okay, when do we use division versus multiplication? So at this point, we've used multiplication for everything. So when do we bring division into this situation? Okay. All right. So that's what we're going to dig into here, because I wanted to set the basis first before we dug into what the real question is. And that is, there is some type of a ambient correction that they want to make, and they want to know when they have to use multiplication or when they can use division. And I'm going to explain that right now. But first, we need to run a sponsor ad. So we're going to run a sponsor ad from our sponsor for today's show, which is Electrician Pride, for all your goodies. So I'm going to run that episode, and then we're going to get into answering this question. Today's show is sponsored by electricianpride.com, your one-stop shop for electrician-specific t-shirts, hoodies, phone cases, mugs, die-cut stickers, leggings, and so much more. Featuring unique designs for electricians, journeymen, and master electricians, as well as electrical engineers and electrical inspectors. For more information on all the products that are available, visit us at www.electricianpride.com today. Okay, so the next question we're going to deal with was sent to us through Ask Paul. Again, you can go over to paulabernathy.com and submit your questions. It says, Paul, when I have an ambient temperature question, when do I divide or use multiplication? How do I know which one to use? So this tells me that what they're doing, since they made reference to an ambient temperature correction, is that they're sizing a branch circuit. Now, of course, this can apply to feeders and services, whatnot, but we're going to take the liberty of saying, okay, let's talk about how we would do this for a branch circuit. And it's going to be the same regardless of whether it's a feeder or service. It's the same concept. But we're going to keep it simple. We're going to talk about it in terms of a branch circuit and how to size these conductors. And we got a bunch of things that we got to take into consideration. So if you got your little scratch paper there, you got to realize that we're going to be dealing in 110.14c. We're going to be dealing in 210.19a1a and b. And we're going to be dealing in 240.4, obviously. And we're going to be dealing in 310.16, the table for ampacities. And we're going to be dealing with 310.15b1. And so that's when you're dealing with the ambient temperature correction. So there's so many variables that are in this question that the electrician has to understand how to maneuver and how to work through. So we're going to kind of cover it. And what I'm going to do is kind of a mini derating demystified. So if you haven't watched that video, it's over on our channel under the playlist for calculations. Watch my derating demystified video. You'll get a lot out of it. And it really covers these adjustment and correction applications. But I want to do an example today to answer this gentleman's question and kind of give clarity to his question. Now, the short answer to this is, for those that just want the short answer, is anytime I'm given a conductor size in a question and I already know the conductor size, and I can go to 310.16, and let's say it's 9-degree rated insulation, I can choose the conductor from the 9-degree column, provided it is 90-degree rated insulation. That allows me to do that in 310.15a. And then I take that full ampacity of that conductor under the 90 degree, and then I multiply that by my adjustment or correction value, depending on if I have more than 3 current carrying conductors, or my ambient temperature is other than 30 degrees Celsius, 86 degrees Fahrenheit. So multiplication would assume that I already know the conductor size that's given to me, and then I can multiply it by those adjustments or correction values in order to find out what my new ampacity of a conductor is, and then I can determine whether or not that can actually handle the load in question. Okay, so that's multiplication. In division, if I'm given the actual load itself, and I still have these adjustment and correction issues that I need to correct or adjust for, then I would take my actual load and I would divide it by my adjustment or correction factor value, and then it will give me a certain amp value that then I'm going to go to the 9-degree column, assuming my insulation is rated for 90, and then I'm going to search for a conductor that can handle that load, then that's how I get the size of the conductor. So depending on what you're given, you can use division or multiplication to work it, as well as quantify and make sure that your answer is correct by using division or multiplication. So that's the short answer. And if you understand that, then you really don't have to listen anymore. However, there's many people that want the down and dirty involved in this. So that's what I'm going to go into now if you want to continue to listen. And of course, I appreciate everybody that listens, and hopefully I explain it in a way that you can understand it. All right, so let's do this. We're going to size some conductors now based on a condition of use. And the question said about ambient temperature. So I gave you my variables. They were 28 amps of non-continuous load, although I'm going to explain to you what happens if it's a continuous load. But in our case, it's 28 amps of non-continuous load. All the lugs are rated 75 degrees C at both ends of the circuit. The ambient temperature in question is 108 degrees Fahrenheit. Those are all of our factors that are involved in this question. Okay, so we know the load. We know the conductors, THHN, which is 9-degree rated insulation in a dry. So we know that, and this is a dry location, so we're good. The lugs are 75. We're good. And the ambient's 108. Okay, first things first. Let's go and find out what we've got to do as far as our terminal limitations in 110.14. So we open up our code book. We're going to go to 110.14 because there's a lot of people that say, okay, Paul, this is 28 amps. You're going to have to pull ampacities from the 60-degree column because 110.14C1A says that. It says terminal provisions of equipment for circuits rated 100 amperes or less or marked 14 through 1 AW conductors shall be used only with one of the following. Okay, so in our question, we didn't say what conductor size it was, right? But we were given an ampacity value. And our ampacity value here is obviously much less than 100 amperes. So we know that we're going to be in 110.14C1A. The question is, do I use the ampacity values in 310.16 under the 60-degree column or under the 75-degree column when it comes to the terminal limitations? Remember, we're using 90 for adjustment and correction, but the terminal limitations are 60 and 75 for most cases. So our question is, since our lugs are rated 75, our conductor's insulation is rated 90, are we required to stick to the ampacity values that are under the 60? Now remember, we're not talking about non-metallic sheath cable, which is limited to 60 under 334.80. We're not talking about that. We're just talking about THHN being pulled in a raceway. It's 28 amps of load, 75-degree lugs, and 108 degrees Fahrenheit temperature. You with me? All right, so because our insulation is rated 90, because our terminals are rated 75, I want you to look at 110.14 C1A3. Now, C1A3 is saying conductors with a higher temperature rating, thus that 90-degree THHN, if the equipment is listed and identified, and we said the lugs they're rated for 75, for use with such conductors. Okay, so under this situation, if I didn't know what the insulation was, if I didn't know what the lugs were, and it was 100 amps or less, and it was sizes 14 through 1, then I'm going to be stuck at 60 degrees C column. But because I know all the variables, because I know the terminals are rated 75, because I know the insulation is rated at 90, which exceeds 75, I am okay to use it at the 75-degree limitation in 310.16, and I don't have to stay stuck in the 60-degree column. That is probably some of the hardest things for people to grasp onto and realize that. Okay, so 75-degree column, we're very much in that with 310.16. That's the terminal limitation column. Even though we're going to use the 90 degree for adjustment and corrections, we're definitely going to make sure that we keep the 75-degree column in mind as we go through this, okay? All right, what's the next thing we want to do as our little journey here? So we understand that. We're okay in the 75. The next thing that we want to look at is what gives me the permission to use that 90-degree rated insulation and that ampacity that corresponds with it under the 90-degree column of 310.16. What gives me that permission? Well, the next thing in our journey is we want to jump to 310.15a. Now, under 310.15a, which is referencing ampacity tables, you'll see the general provisions, but we're more more interested in the second paragraph, and that is where it says, the temperature correction and adjustment factors shall be permitted to be applied to the ampacity for the temperature rating of the conductor. This directly gives me permission to use the ampacity values under the 90-degree column because it is THHN. Now, if it wasn't THHN and the insulation rating was, say, THWN, then that would be only under the 75. And so my adjustment and corrections would have to come from the 75. But in this case, it's THHN, it's rated 90. I can use that ampacity for adjustment and correction purposes. However, it goes on to say, you can do this if the corrected and adjusted ampacity rating of the conductor does not exceed the ampacity for the temperature rating of the termination in accordance with the provisions of 110.14c. And we've already done that. We know that we're in 75. So again, we're going to adjust and we're going to correct. We're going to look at our load. We're going to look at the new conductor's ampacity, but we're going to make sure we do not exceed the value that's in the 75-degree C column, because that's what got us there in 110.14c. Right? And we already did all that. So we're feeling pretty good now, right? We know that we can use the 90 for adjustment and correction. So let's kind of work it through. So that's the second thing we looked at. Okay. Now, the next thing that we want to look at in this little journey is 210.19. And why is it important? Because that is where we start to learn what our sizing requirements are for our branch circuit conductors. Now, remember, this would be the same if it was in 215 for feeders or 230 for service conductors. These rules I'm getting ready to talk about are exactly the same. And it's easier for us to discuss this with the branch circuits. It's just easier to wrap your head around it. Let's say you got your code book. We want to look at 210.19, A1, A, and B. Now, we're going to read 210.19 A1 because that's the general premise, and we have to follow the general rule to understand how we're going to size these conductors, the minimum size, because that's what this is. 210.19 is conductors, the minimum ampacity and size, which go hand in hand. So the general rule here is, it says the branch circuit conductors shall have an ampacity not less than the larger of 210.19 A1A or A1B and comply with 110.14c for equipment terminations. Now, we see this again. It reminds us of these terminal limitations, the weakest link concept. Now, in our case, all of our lugs were rated 75 degrees C. Now, I'll remind you that if one lug was rated 75 and the other was rated 60, then the weakest link means that we would have to be default at the 60-degree column because there was a weak link here. There was a 60-degree rated terminal. In our case, they're all 75, so we're okay. And that's what 110.14c told us. We're okay. All right. So in this case, there's an or in there. What does that or mean? The difference between 210.19 A1A or A1B is going to force you to do a calculation and determine the size of conductors under each consideration, A1A or A1B, and you're going to take whichever results in the larger conductor size. Make sense? Now, let's look at A. A says, where a branch circuit supplies continuous loads or any combination of continuous and non-continuous loads, the minimum branch circuit conductor size shall have an ampacity not less than the non-continuous load plus 125% of the continuous load in accordance with 310.14. All right, so let me give you some things to think about here. Even though our question had an adjustment correction in it, if this was 28 amps of continuous load, then we would ignore the adjustment at this time. We're simply going to size the conductor for the continuous load in order to determine what size we need to have. And since our question also has an ambient temperature, then we're going to compare that to B, which is different than A. So let me throw this scenario out at you, just to throw it out at you. Let's say that this was 28 amps of continuous load and not non-continuous load. So if it was continuous load, but we still had the ambient temperature involved, we're ignoring the ambient temperature for this first one. Because the first one says take the continuous load at 125% and size your conductor. So I'm going to take my 28 amps of continuous load. That's what it is. And I'm going to multiply that by 1.25, which is 125%. And that is 35 amperes. Okay, so that's my value. So the first thing that I would do is go to where's my terminal limitation, 75. People say, well, why wouldn't you use the 90? Because in this example, I'm not doing any adjustment and correction. I'm following what it says. I'm saying take the continuous load at 125%. And because we're not doing adjustment or correction, we go straight to the terminal limitation column, and that is 75. There's no way we can use the 90 for this. Now, we're going to do it in a minute, but right now, we're just going to the 75. So under the 75, it looks like for continuous load that I would need to use a 10 gauge. That is 35 amps. All right, so it's good for 35 amps. That's a continuous, so that would be a 10 gauge. And that would be our conductor under 75 degrees C. Now, we all know that we still have limitations for 30 amp conductors being protected at 30 amps, 10 gauge at 240.4. We get it. But we're sizing conductor right here. And it's basically, we only had 28 amps of load, but we're sizing the conductors based on what? Based on 125%. All right. So in this case right here, if you're using this value, it would be 35 amps is 125%. So that would be a 10 gauge, and you would protect that at what? 30 amperes. Terminal limitations. Now keep in mind that there are other allowances for things like motors or HVA systems and 240.4 that you can apply. But for the general rule here, a 10 gauge protected at 30, 12 gauge at 20, 14 gauge at 15. Those are called small conductor rules, and they fall under 240.4D. Okay. So in our case, that would be the conductor. So it would be a 10 gauge. We're just sizing conductors right now. That's all we're doing. It's 10 gauge. Now let's go back to our equation. Now we want to look and say, okay, so we picked the conductor size for the for continuous load. We did it. Understanding, again, we have to protect it at 30 and all that yada, 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 unless, of course, it's motors or whatnot. But now we're going to go on to 210.19A1B. And this is where the OR comes in. And remember, we're still talking continuous load. Our example was a non-continuous, but we're just going to talk continuous load here still. When you're doing B, you don't worry about the continuous load. That was already done in sizing for A1. I mean, for 1A, excuse me. We're in 1B now. This says the minimum branch circuit conductor size shall have an ampacity not less than the maximum load to be served after the application of any adjustment or correction factors in accordance with 310.15, and more specifically 310.15B1 or 310.15C1, depending. B1 is a correction and C1 is an adjustment. Now, in our case, we got to go back now to what our original variables were. It's 28 amps of actual load, so we need a conductor that can handle 28 amps of actual load. At this point, people will say, well, what about that continuous load? We only use that fictitious additional 25% for sizing the conductor because of the continuous load. The load is still 28 amps. That didn't change. We just followed what the code said and sized our conductors. But when we're under B here, we just need to make sure that after adjustment and corrections, I have a conductor that can still handle the load at hand, and that is 28 amperes. So let's kind of do that. So what do we do? All right, so that's where we're going to do this next calculation. And what we're going to do is we're going to look at the variables in the calculation. And the first thing that we're going to do is we're going to say, okay, what do I got? I got 28 amps. I've got terminal limitations. I've got all these things that I need to work out. So the first thing that you would think in your mind is, okay, well, since I'm doing an adjustment, I'm doing a correction for ambience, the first thing I need to do is, what is the value that I'm going to use in my equation? And we haven't even talked about multiplication versus division yet. We're just simply going, the only multiplication we did was to take the the 28 times 125% in order to find out what the continuous load was and size the conductor accordingly. And that's how we picked the 10 gauge under 210.19A1A. We've done that and we wrote that down. But now we have to compare it. Now under B, we forget about that continuous load. Now we bring in the correction application. So the first thing I need to do here is say, okay, what's the value that I'm going to use with this conductor? Well, it is 108 degrees Fahrenheit. Obviously, table 310.16's Ambient deal with 30 degrees Celsius or 86 degrees Fahrenheit. So I need some kind of correction. Well, the first thing that you're going to do is you're going to go to table 310.15B1. Now, this table is your ambient temperature correction factors, and it's based on 30 degrees C. Now, this question comes up from time to time. Paul, why use B1 versus B2? Well, that's because B2 table here deals with 40 degrees C basis. And that's if you're using conductors in tables 310.18, 310.19, 310.20, 310.21. Those tables are based on a baseline of 40 degrees C. But 310.16 and 310.17 are based on the baseline of 30 degrees C, 86 degrees Fahrenheit. That's why we're going to use 310.15B1. And for most cases, you're going to be dealing with conductors and ampacity adjustments and corrections. For normal everyday applications, for normal building wire, you're going to always be using 310.15B1 for any ambient corrections that you need to do that are other than 86 degrees Fahrenheit or 30 degrees Celsius. You with me? So in our case, we said it was 108 degrees Fahrenheit. And we also know that our conductor insulation is THHN, so it's rated for 90. Now, where do you get the ratings for insulation, in case you ever wondered? You're going to go to 310.4A, and in that table, you're going to see all of the temperature ratings for all the different types of insulation types that are used in building wiring. Now, it used to be 310.104, but under the change that took place in the 2020, it got reorganized to a much easier flow, much easier to understand. Now it's at the very front where it needs to be, and that's a real important table because that shows you, for example, that XHHW is only good for 75 in a wet, but 90 in a dry. Even though it has two H's, it still is not rated for 90 in a wet unless it has the -2 on the end of it. That's important stuff to know, especially if you're going to do adjustment and corrections from a 90 degree. You need to know that the conductor's insulation is actually rated for 90 degrees. Otherwise, you'd have to do it from the 75. You with me? All right, so in our case here, we know it's THHN. So we're over on table 310.15B1 because we're trying to find our correction factor value to use in our equation. Now, since it's 90 degree rated insulation, you're going to be in the 90 degree column. And since we're using Fahrenheit, we're going to be using the column on the far right. So I'm going to come down until I find the value that falls for 108 degrees Fahrenheit. And it looks to me that 105 through 113 is where this value is going to fall. Then you move to the left, and that tells me that it lines up with 0.87. That is going to be my new correction factor to use for this conductor based on this condition of use. So now let's kind of go back to the ampacity values. Okay, so we're back at 310.16, and we know we're using THHN. So what we're going to do is we're going to come down the 90 degree column because our insulation is rated 90, and you're going to notice these ampacities. Now, the first thing that somebody might stumble on is they might say, well, wait a minute, it's 28 amps of actual load. Why can't I use a 12 gauge? Well, yes, that is 30 under the 90, but remember what we said about terminal limitations? The values can exceed the values under the terminal limitations in the 75 degree column. Remember that we got there by looking at 110.14C earlier on? Well, you'll notice under the 75 degree column that a 12 gauge is only good for 25 amps. So our load is 28. So immediately we automatically, without doing any calculation, we know that it could not be 12 because of these terminal limitations. So immediately you drop down to 10. Now 10 has 35 amps under 75 degree column. Easily going to handle our 28 amps. We're not going to exceed the values of the 75 degrees C. We're good to go. However, we now jump straight to the right to the 90 degree value, which in this case for 10 is a 40 amp rating. And this is where we're going to start doing our multiplication first. And I'll show you how division can be used if depending on what values are being given to you. But let's start from this. So I know that that's 40 amps. So I'm going to do 40, and I'm going to multiply that by my correction factor, which was 0.87. Remember we got that earlier? Remember, anything that's in this value is going to be multiplication that is 1.00 or less is going to actually reduce the ampacity of my conductor. So in this case, I'm going down. I'm using multiplication to go down in my sizing. So I'm going to take 40 and I multiply that by 0.87. And that gives me 34.8 amperes. So now this is what my conductor, my 10 gauge, can actually handle. And so if you go under the 75 degrees C column, you will see that it was originally rated 35. So now it's been reduced down to 34.8. Now, for no reason can I ever exceed the 35 anyway. We've learned that because of everything saying not to exceed the values under your terminal limitation. But in this case, that 35 has now been reduced to 34.8. Well, in our situation, what it said for us to do in 210.19a1b was that after the correction, I have to have a conductor that can actually handle the load. What is the load? It's still 28 amps. That is the load. So in this case, I would still be perfectly fine under the 10 gauge. In fact, because of the small conductor rules, I would terminate that 10 gauge on a 30 amp overcurrent device. Again, there's exceptions to this rule. If you're dealing with motors or HVA systems, you got to go look at 240.4 and you will see the allowances that you have. But in this case, we're just talking about normal branch circuit. So that 28 amp conductor is protected by a 30 amp overcurrent protected device because there isn't one that corresponds in 240.6a for 28 amps. So it allows me to go up to the 30 amp device and everything is great. And a 10 gauge is perfectly fine to handle my 28 amps of load. Now, the key here was to size the conductor, and that was a 10 gauge. Now, in this scenario, I now would compare the equation that we did with a continuous load with that of the one with just dealing with the ambient correction. Whichever one results in the larger conductor is the one we're going to choose. In our case, they both resulted in a 10 gauge. So 10 gauge is clearly our choice. Okay. Now, that is kind of the gist of the application. But now I want to show you how division can come into play. Now, what in this same situation, what if I'm given a load value of 28 amps? And I'm given all these conditions, the 75 degree lugs, 180 degrees Fahrenheit, everything's the same. But in this case, I'm given this 28 amps. And I want to size the conductor. I have no idea what size that I want to do. So I can take this 28 amps. Now remember, division works your way up. And since we have an a correction that we're going to do here, and our conductor's rated 90, then ultimately we're going to search for our necessary conductor under the 90 degree. But to start, we're going to do our 28 amps, and we're going to divide that by 0.87. Remember that 0.87 was the ambient correction at 108 degrees Fahrenheit. So I take that 28 and I divide that by 0.87. And that is 32.18. So I have to have a conductor that is good for 32.18 amperes. Now I'm going to go to the 90 degree column because remember what it said in 310.15a that I can use the 90 if I'm doing adjustments or corrections. Well, I am. I'm doing an ambient correction. So I'm going to search for a conductor under this 90 degree column that is good for 32.18. And so you start from the left, THHN, 90 degree column, you go down, you'll notice that, well, the 12 is good for 30, but that's not going to work. We've already determined that anyway, but that's a pretty quick way to determine. And then you get to the 40. Is that 40 greater than 32.18? Absolutely. Absolutely. Now, so that would tell me that I would need a 10 gauge. So that's the way you would use division to do that. Now, you can check yourself by using multiplication. And in the multiplication, when you're checking yourself, you're going to use the full value from the 90 degree column, which is the 40. And you do 40, like we did before, 40, and we'll do times 0.87, and that is 34.8. That's what we got before. 34.8 is more than enough to handle 28 amps of actual load. See how that works? So you can use division to go up, multiplication to check your work and go down. And some people ask me, okay, Paul, how does that work if you've got also an adjustment? Okay, so let's introduce this question. Nothing changes in the variables except for the fact that we're going to say that we have 4 current carrying conductors now. How does that change? Well, we're not going to do anything different except for now we have the additional requirements of adding a adjustment factor under 310.15c1. And that's because we have the number of current carrying conductors that exceed 3. Remember now, 310.16 is only dealing with there's not more than 3 current carrying conductors. Okay, so that's 3 or less. It also only deals straight from this table if you're dealing with 30 degrees C, 86 degrees Fahrenheit. So we've already addressed the ambient temperature issue, but now we've interjected the fact that we've got 4 current carrying conductors. So we're exceeding 3. So again, we have to do an adjustment. So you go to 310.15c1, and for those that are in the 2017 code, that would be 310.15b3a is where you would find that. It's just been a slight change in the location for the 2020. No big deal, didn't change anything. Okay, so if you look at 310.15c1, you'll see that when you have 4 to 6 current carrying conductors, that there is an 80%. And you're going to have to apply that adjustment. Start from the right, move 2 decimal places to the left, and put a period. That is 0.80. You might already know how to do this, but that's how you convert this. Start from the right, move 2 places to the left. You're converting this to a decimal value. So in this case, it's 0.80. So there's no real change here. So let's assume we were in the same scenario because I want to show you how you would use division to do this and how multiplication can quantify it. Same 28 amps. But now I have 108 degrees Fahrenheit and I have 4 current carrying conductors. Well, it's no different. Using division, I can work my way up to selecting a conductor size if I didn't know what conductor I wanted. I still have to handle the 28 amps after the adjustment and correction. That's the golden rule there. So I'm going to go 28, and I'm going to divide that by 0.87 that we did earlier, okay, which gave us 32.118. Then I'm going to divide that again by 0.80. And that gives me 40.22. So basically you're doing 2 of them in there. You're going 28 divided by 0.87 divided by 0.80. And that's your ampacity that you're going to be searching for under the 90-degree column. So remember, division, you work up. Multiplication, you're working down in this scenario. So in this case, I'm going to go to the 90-degree column, still THHN. I'm going to go down and see, well, a 10 gauge is only good for 40. So I'm going to go to a 55 amp. So I have now bumped myself into an 8 gauge for this application. Now, how can you check yourself? Well, let's check the 40 amp rating of that THHN first, because you might be saying, well, why can't I just still use the 10? Well, if we use the 40, now we're using multiplication now. We pick the ampacity from the column, and we work now multiplication. Now we're working down to see if we now have a conductor that can actually handle our load. So 40 multiply 0.87 times 0.80 equals 27.84. It's not going to work. I need a conductor that can handle 28 amps. This conductor now can only handle 27.84. There is no rounding here. This is not a calculation that you would do up in 220 where you were able to round 0.5 and greater round. No. The conductor's ampacity is what it is. So in this case, you wouldn't go to 28. It would be 27.84. That is the maximum that this conductor can carry at this point. And we needed to have what? At least 28 amps. So that 10 is not going to work. So check your math now. Go to the 8 gauge. It's good for 55. 55, multiply that by 0.87 times 0.80. And that conductor's new ampacity value is 38.28. Okay? So that is the value now of this conductor. And that can easily handle the 28 amps. Nothing at C exceeds the 75-degree column rating because, again, the 8's good for 50 under 75. So we're only going to be putting 28 amps of load on here. Even though the new conductor's ampacity is 38, we're not trying to use it at 50 because now it's only good for 38.28. So at the end of the day, what? We're okay. because we only needed 28 amps out of it. But after the adjustment and corrections, we needed to make sure that we had a conductor could handle the actual load. And that's what we've done. You with me? Okay. Now, how would this have equated if it was still 28 amps of continuous load versus this condition where we had both an adjustment and a correction? Well, that's where this gets real important, because you remember under the 125% of that 28 amps, that was a 10 gauge. Well, that was 210.19 A1A. But remember, you have to compare it to A1B. And A1B, if it had an adjustment and a correction factor, then that would have resulted in an 8 gauge. So ultimately, at the end of the day, do you choose the 10 or do you choose the 8? You choose the 8 because that is the greater of the two comparisons in 210.19 A1A versus A1B. That is a great example of how that applies depending on your conditions of use. Just remember that you don't use the continuous load in the A1B portion. You only do that in the A1A portion. And if no continuous load is present, then you jump straight to A1B and utilize that. Okay? All right, so hopefully you got something out of that. I've kind of gave you a little bit of everything in that episode, so it kind of pulled everything together. If you have any questions, remember, you can go to www.paulabernathy.com and ask your questions. That's what I'm here for. I designed this so that it segregates your questions into a way that I can answer them and get to them as quickly as possible. So hopefully you got something out of that. This episode went a little longer than normal, but at the end of the day, hopefully you got something out of that lesson. Until next time, stay safe. God bless. And of course, we did not talk about all the possible variables involved. So don't come to me with questions and say, well, you didn't say this and this. Only germane to the question that was asked. And I'm only going to answer the questions as they're asked. Until next time, stay safe. God bless.